Hello guys. Before we start isolating processes, changing host names, or playing with network interfaces, let's take a step back and understand the big picture. When people talk about containers, what they are really talking about is namespaces. A Linux container is not just magic. It's not a VM. It's not a special binary format. It's just a regular Linux process, but with one superpower. That process is placed inside several namespaces, and suddenly it behaves as if it's running on its own tiny computer. This is why namespaces are root of all container technology. Docker, Containerd, Kubernetes. They simply orchestrate Linux features that already exist inside the kernel. So before we jump in, let's understand these namespaces visually. So think of the Linux kernel right here as a tree, one giant environment where all processes live together, no isolation. Everything can see everything. Namespaces are like six strong roots that carve out separate environments. Each root creates a different dimensional isolation, process, networks, mounts, and when you combine all of them, you get a fully isolated container. Let us quickly walk through each root that are different namespaces in the form of root. So the first namespace, that is PID namespace. So without PID namespaces, a process inside a container would see every process on the host. Imagine ps aux showing your host systemd, kubelet, docker daemon, chaos. What PID namespace does is this namespace isolates the process tree. Inside the container, PID1 might be just your app. Outside, PID1 on the host will be a systemd. This is what makes a container feel like it's running its own init. Second namespace, that is your net namespace. This is one of the most important namespaces. Our net namespace gives a process its own IP address, its own routing table, its own network interfaces. Without it, containers would not be able to have their own IP or connect through isolated virtual networks like VTEX, pairs, and bridges. Kubernetes heavily depends on this. A pod shares one net namespace, which is why all containers inside a pod share a single IP. Here, one pod is equal to one IP address. So this functionality of Kubernetes comes from this net namespace. Keep it in mind. The third namespace, that is mount namespace, MNT. This namespace gives a process its own mount table. That means its own root file system, its own volumes, and its own mounts. So when Docker overlays your file system layers into container root FS, all of it works because of MNT namespace. The fourth one is UTS namespace. This lets the container have its own hostname. So inside Docker, if you type hostname, it will have a container ID. Inside a Kubernetes pod, if you type a hostname, it will have the pod name. This namespace is tiny but crucial. It gives each container its own identity. The IPC namespace, that is the fifth one. This isolates shared memory and message queues. Without IPC isolation, processes inside containers could read shared memory segments of the host or other containers, a serious security issue. Sidecars in a pod often share IPC namespace for performance reasons. The last one, that is user namespace, a user and permission isolation. This is what maps container root to a non-root host user. With user namespace, root inside container is equal to non-root on host, perfect for unprivileged containers. So how Kubernetes uses these namespaces differently? Docker isolates all 6 namespaces for each container. But Kubernetes does something more interesting. In a pod, a container shares some namespaces, that is, net 1 IP per pod, as we spoke here, then IPC for fast sidecar communication, the UTS for consistent hostname. This is why a pod behaves like a small virtual machine with multiple processes inside it. A pod is a logical host, not just a group of containers. Keep that in mind. So in this 4-part series, we are going to bring these namespaces to life. We'll start from a pure Linux using the unshare, LSNS, and /proc. We'll see isolation happen right in front of our eyes. We'll see the same concepts in Docker as well. And finally, we'll see how Kubernetes relates, how pods are built by combining containers and namespaces in a very clever way. By the end of this 4-part series, maybe, you won't just use containers, you will understand the foundation that makes containers possible. So let's start with the UTS namespace, a hostname isolation powering containers and pods. So what is a UTS namespace? A simple explanation, UTS stands for UNIX Timesharing. This namespace isolates two things: hostname, what hostname command shows, node name, node identity used by some kernel calls. This means every namespace can think it has its own hostname, even though the machine is the same. This makes container names like, for example, Nginx or whatever container names happen possible without changing the real hostname. So let's start by just doing a small demo how the hostname command on your OS, how it works. So I'm using a killer coda environment. You can use the labs that are there on their uh, website where they provide you with an environment which is already set for you. They have environments for Kubernetes, for Docker. There are n number of environments and also scenario based labs. So do try it out. It will help you. So here, what I'm going to do is first I'm just going to see what hostname command returns. So it will return you the hostname that is set. For you, it might be something else, that whatever you have set. On my local system, it returned Shashank-host. So it will be different for you. This will return a hostname. So you are on the host machine. So now what we can do is we can use the unshare command to create a new UTS namespace. So the unshare command is sudo unshare -4 -UTS and bash is the process. So if you see now you have entered into the UTS namespace. So if you see it will still return hostname as the one that is there, but you are not in that namespace. You are in the namespace that you created for UTS. So to verify that, what I'll do is I'll do the sudo hostname and give it demo-container. So now the hostname is demo-container. Now we will exit out of this and go to the host machine. So now you should get a hostname as control plane, one which was there before creating the namespace. So if you do hostname, here you are on the main machine and it is returning the hostname of control plane. So this allowed you to create a isolated UTS namespace. So the processes inside this namespace can have a different hostname without affecting the host. So as we saw, right, the host had a different hostname without touching the one that is there in the namespace, and the namespace had a different hostname without affecting the hostname that is there for the host. So inside that new namespace, we were effectively like in a sandbox. we were able to change the hostname, and this change was visible only to those processes within that same UTS namespace. So after exiting the shell, we return to the host original context. The changes that we made there were gone, and it didn't affect the host or the namespace or the processes on the host, proving the namespace provided a secure boundary. So this is the power of UTS namespaces. Each isolated environment can have its own hostname without touching the real host. Containers rely on this illusion to give each container a meaningful identity. So now let's see from the Docker's perspective how containers use UTS namespace. Let's see the Docker mapping. So we'll just start by running a Alpine container. We'll call it as UTS demo. So it is, we'll run this. So we'll just name it as UTS demo and that's it. So it is running. So now let's exec into it, and so let's see the host name. So this is the host name. So if you might get a question what this host name is and what it is coming from, let's see. So let's exit out and see the Docker PS. So it is the container ID that it returns. So it is clear it is coming from host name. The host name came from the Docker assigning the container's ID. So as you can see, it is the container ID and it is returning the container ID as its host name. So how is this happening? So the answer lies in the Linux fundamental, what we just learned about UTS namespace. Docker is using the Linux kernel feature of UTS namespace to provide isolation. So think of it as a private universe for your container's hostname. The processes running inside a UTS namespace can have a completely different hostname from the host system and other namespaces. So now, as you can clearly relate, there is no Docker magic. It's just the basic Linux fundamentals that Docker is implementing. So now let's locate the container process on the host. So to investigate, we will use the docker inspect command and get the process ID in a variable. So we will do the inspect on the UTS demo that we just spun up. 12775 is the process ID of the container. So next we'll find it in the /proc system in the ns UTS folder. So this gives you the UTS, that is 402.65.32.829. So the output tells us everything. So let's break it down. So when you did a ls-l on the proc file system with the container process ID, it gave you a output and it was a symbolic link. The file represents the UTS, that is UNIX Timesharing System over here, which specifically handles the host name and domain name for a process. This indicates it's a symbolic link, meaning UTS is a pointer to an underlying kernel resource here. This unique identifier for the namespace. The container process is inside its own isolated UTS namespace, separate from the host. So here we used unshare and we used Docker to do the same. They are using the same principle. So in UTS, for UTS using unshare, a new UTS namespace was created. The host name is initially inherited from the underlying host and it can be changed. While using Docker with the Docker command, a UTS namespace again is created. The host name is set to the container ID. The namespace persists as long as the container is running. So both approaches were using the same underlying principle of UTS and leveraging UTS, leaving the host name unchanged and providing isolation. So the Docker automates this exact process for you. So when you run Docker run, Docker is essentially doing three things for you automatically regarding the hostname. Creates a new UTS namespace, like how we did it with unshare minus minus UTS, sets the hostname within that namespace to the container's ID, and starts your specified process inside that new namespace. So Docker automatically puts every container in its own UTS namespace. That's why each container gets a unique hostname. Next, we will see how Kubernetes builds on top of the same concept. So now let's see how UTS namespace behaves for the Kubernetes pod. We will see that doing a practical demo. So the UTS namespace isolates two specific system identifiers, the hostname and the domain name. So in a container, it runs its own set of namespaces for each container. But whereas in Kubernetes, it has a different model to how it behaves for a specific container. In Kubernetes, there is a pod in which there can be one or two containers. So let's see how the UTS namespace behaves in this scenario. So in this demo, we will explore exactly how the UTS namespace handles things inside a pod. So our doubt of container in same pod share a same hostname will get clear by this demo. In this demo, what we will do is we will deploy a pod which will have two containers within. After deploying that, we will check the hostname for each of the container, which we expect to be the same. Also, we will inspect the underlying namespace identifier to confirm the findings. So this is our pod manifest that is you can see on the screen. So we have two containers in this, that is C1 and C2. And we will then exec into both these containers and see the hostname. So let's go ahead and apply that. We'll do a kubectl apply -f and uts demo pod.yaml. So the pod is created now. So now let's exec into the pod and see the hostname for C1 container. So it is UTS demo pod as we expected, the same name as the pod name. Let's do the same for the C2 one. See, both of them are sharing the same hostname. So this is a proof and a strong evidence that both containers see the same system identity. So we proved it by checking the hostname and both of them are using the same hostname. But now let's inspect the namespace file itself. /proc /self /ns /uts file in a Linux process is a symbolic link to the actual namespace instance. We will do that using the readlink command. We will show the namespace type and its unique inode number. If the inode numbers for both the containers match, the containers are sharing the exact same namespace in the kernel. So let's go ahead and do that through a demo. So now we are using the readlink command on the UTS namespace file inside each container C1 and C2. So let's do it for C1 first. So it has returned this UTS number as you can see. Now let's see if it is the same for UTS for C1 for C2 container as well. We will change the C1 to C2. Yeah, as you can see, the number is same. So the return output is a same inode, which is a shared UTS namespace. This is a definitive proof that both the containers are using the same UTS namespace. So all containers in a pod share a single UTS namespace by default. They are designed to be cohesive unit of execution. So here's the whole journey we just explored. We started by checking the host original name. That's our baseline, the identity of a real machine. Then we used unshare to create a brand new UTS namespace which instantly dropped us into an isolated shell. Inside the shell, we changed the hostname to demo container. And just like the slide, the change was completely contained within that namespace. The host outside stayed untouched. This simple 5-step flow is exactly how containers work behind the scenes. Docker gives each container its own UTS namespace, which is why every container gets a unique hostname. And Kubernetes goes further. All containers in a pod share the same UTS namespace, so a pod feels like one logical unit. And that's the power of UTS. Tiny mechanism, massive impact. Identity without interference. Isolation without complexity. So in the next episode, we move from identity to process. We will explore PID namespace in the next episode. So stay tuned. Thank you.